Hello everyone, welcome back. In this video, we will be covering the mean value theorem, section 4.2. So before we get into mean value theorem, let's see what Rolle's theorem is about. Rolle's theorem, let f be a function that satisfies the following three hypotheses. Number one, f is continuous on the closed interval AB. Number two, f is differentiable on the open interval AB. And f of A equal to f of B. Three hypotheses. The function f should be continuous on the closed interval, differentiable on the open interval, and f of A equal to f of B. The height at A must be same as height at B. Height at A equal to height at B. Y values at A and B are the same. Then there is a number C on the open interval AB such that the derivative equal to 0. The derivative at C equal to 0. This is what Rolle's theorem is. So in all these four figures below, we notice that the function is a continuous function, which doesn't have a break or a hole. Then differentiable means that the function, the graph, will have tangent at every point. You will be able to draw a tangent at every point on the graph. That means it's differentiable. So you have a graph, the blue line. It is a constant function. It is continuous and it's also differentiable. And the height at A is same as the height at B in the graph. So you notice that every point in between A and B, you can say that there is at which the derivative equal to 0. So we have to just say there is a number C on the open interval AB such that f prime C equal to 0. The first figure, every number between A and B will satisfy that condition. Then the second graph, it's continuous and differentiable, and the height at A is same as height at B. Then definitely there is a peak attained at C. So it is at C, the derivative equal to 0. There is a horizontal tangent there. The third picture, it's definitely continuous and it's differentiable. And the height at A is same as height at B in the graph, right? The height at A is same as height at B. Then we notice that there are 2 points at which there are horizontal tangents, C1 and C2, at which there is a peak, there is a valley. At both places, the derivative equal to 0. So we have to show there is a C at which the derivative equal to 0. You see another function, fourth graph, and it is continuous on the closed interval AB, differentiable on the open interval AB. The height at A is same as height at B. And you will see a valley here at which the derivative equal to 0. So continuous, differentiable, and the heights being equal at the endpoints are the three requirements for three hypotheses for Rolle's theorem. Then what is mean value theorem? Let f be a function that satisfies the following hypothesis. Right? F is continuous on the closed interval AB, and f is differentiable on the open interval AB. Then we don't have the third hypothesis of Rolle's theorem. The result is that the conclusion is there is a number C on the open interval AB such that the derivative at C, f prime C, equal to f of B minus f of A over B minus A. So keep in mind, if you have 2 points, let's say A and B, if the coordinates of A are A, f of A, let's say they are points on the graph of y equal to f of x, and B, f of B are the 2 points on the graph, then what is the slope of this line AB? Difference in y coordinate over the corresponding difference in x coordinates, which is in this case f of b minus f of a over b minus a. So the right hand side expression here gives only the slope of the line join of a and b. Equivalently, this result can be stated as, if you multiply both sides by b minus a, you would get fb minus f of a equal to f prime c times b minus a. So if you look at these two pictures here, what is the difference between Rolle's theorem and mean value theorem? In Rolle's theorem, the heights at a and b should be the same. So they should have the leveling height. In this case, that requirement is not there. So if you notice, the point A and point B are kind of tilted. They're not in the same line. So what it tells is that, so there is you can find out a C in between A and B, at which the derivative, that this line, the pink line, and the line join of AB are parallel to each other. That means the slope of this line, tangent line at C, and the slope of the line join of AB, they are one and the same. This is the slope of the tangent line at C. So what is that? F prime C. That should be equal to the slope of the line join of, the secant line join of A and B. The secant line joining A and B has a slope f of b minus f of a over b minus a. That is the slope of the line join of A and B. And it should be equal to the derivative at C, which is f prime C. Now, in the second picture, the line is tilted, AB is tilted, the height at A is different from height at B. Here you notice there are 2 points. The tangents at those points are parallel to the line join of A and B. Okay. The slope of this line is the same as the slope of this line here, tangent line, they are parallel. The two parallel lines have the same slope, and it is same as the slope of the line join of A and B. So f at C1, the tangent line at C1, which is C1, f of C1, that will be, the slope will be equal to f prime C1. Here it is at C2, f of C2. What is the slope? M is called f prime C2. What is the slope of line join of A and B? Which is fb minus f of A over b minus A. So in all cases, the hypothesis of mean value theorem, the conclusion of mean value theorem is satisfied. Next theorem, if the derivative at any point is 0, the derivative at x, derivative of x equal to 0 for all x in an interval AB, then f must be a constant. So we know that if y is a constant, then the derivative must be 0. The converse is also true. If the derivative is 0, then the function must be a constant function. If the derivatives are equal for all x in an interval AB, then what does this mean? The derivative, the difference is equal to 0. That means f minus g is a constant. So this means f prime x equal to g prime x for all x. So we know f prime x minus g prime x should be equal to 0. So what does the previous corollary theorem says? The derivative equal to 0, then the function must be a constant. So you can write this as f minus g prime of x equal to 0. So if we treat this as a single function, the derivative of that function equal to 0, that means from the earlier theorem, the function must be a constant. So f minus g equal to c, or f equal to g plus a constant. So the two functions differ by a constant. So in this exercise 4.2, there are many problems done in the section videos. So check the video, section video. The practice test number 9 is done there. Then 15, 17, practice final, and even this one. Show that the equation has exactly one root. These are all done, but I'll show you one problem where it says it has exactly one root. I'll show that in this video. But for the rest of the problems, you can get the help from the videos. Practice test 9 is done, practice test 15, practice final 17 is done, and 19 is also done. Let's take up one problem. Prove that the equation x cubed plus x minus 1 equal to 0 has exactly one root. We'll try that one. So the given function is x cubed plus x minus 1 equal to 0. First, let's show that there is at least a 0. There is at least one root. At least one real root. So we can use intermediate value theorem for that. F of x is a polynomial. The polynomial and therefore continuous. Therefore continuous and differentiable. Continuous and differentiable. So let's say we have to show that there is at least one real root. Let's take two values and say f of 0 is equal to -1 if you plug in 0 there. And what is f of 1? It's 1 plus 1 minus 1, which is positive 1. So you have found 2 points, 0 and 1. So for one value, the y value is negative. For the other, it is positive. Because the function is also continuous, you can say that by intermediate value theorem, f of x has a 0 or a root between 0 and 1, because those are the values you plugged in. Between 0 and 1, this is by intermediate value theorem. So we proved the existence of a 0. Now we have to show that there is only one 0. There's only one 0. So let's do this by contradiction. Proof by contradiction. So if possible, let there be two roots. If possible, let there be two real roots. Say for this function f, let's say a and b. What does that mean? F of a equal to 0 and f of b is also equal to 0. So this is actually third hypothesis of Rolle's theorem. So f is, we already know that it's a polynomial, x cube plus x minus 1 being a polynomial, this differentiable and continuous. In fact, over the entire real line, but it's enough if you consider the 2 points A and B for the purpose of the theorem. In fact, we have to say continuous on the open interval, continuous on the closed interval AB, differentiable on the open interval AB. And also you are given, so that means that both two conditions, this is hypothesis 1 and this is hypothesis 2. And you already know that is a third hypothesis, we already said. So we already mentioned that. So by Rolle's theorem, so you have all the requirements that are needed for Rolle's theorem. So by Rolle's theorem conclusion, what does it say? There is a C. There is a C in the open interval AB at which the derivative equal to 0. So what is f prime x? F prime x is the derivative of x cube plus x minus 1. So it is 3x squared plus 1. So what is f prime? C. So x replaced by c. That will be 3c squared plus 1. This is given to be 0 by Rolle's theorem. So what does this mean? F prime c is c 3c squared plus 1, where c is a number between a and b. So this number 3c squared plus 1, the square plus 1, it's definitely positive. So it cannot be equal to 0. F prime c equal to 3c squared plus 1 is always positive. The f prime c equal to 0 leads to a contradiction. This leads to a contradiction. Why does it lead to a contradiction? Because we started off by saying, let there be two real roots, say A and B. Because of this contradiction, we have to say that there cannot be two real roots. So we already said that there is at least one real root. And if there is only one real root, it also means here in this problem, it cannot have more than one real root. What it means in this problem is that this being cubic, the real other two roots must be complex numbers. An equation of a polynomial of degree 3 will have 3 roots. And we said that there is exactly one real root in this problem by contradiction method. And it also, because degree 3 will have 3 roots, the other 2 roots must be complex. So this proves that f of x has exactly one real root. Let's take up one more problem here. Does there exist, problem number 31, does there exist a function f such that f of 0 equal to -1, f of 2 equal to 4, and f prime x less than or equal to 2 for all x? So the question is, does there exist a function with all these properties? F0 should be equal to -1, f at 2 should be equal to 4, and f prime x less than or equal to 2. So this condition here tells us f prime x less than or equal to 2 tells us that even though it is less than or equal to 2, it tells us that f prime x exists for all x. So this tells us that f prime x, or the derivative, exists. And if the derivative exists, then the function should be continuous for all x. Differentiability implies continuity. So the derivative exists means that f of x is continuous for all x. So this is hypothesis 2 of mean value theorem. This is hypothesis 1 of mean value theorem. Only thing is we have to restrict our domain to A and B. So the A and B values can be chosen as 0 and 2, because anyway they are, f of x is differentiable throughout x for all x. The same way it is continuous for all x. So we can restrict our domain and say f of x is continuous in particular on the interval, on the closed interval 0 through 2, and then f of x is differentiable on the open interval 0, 2. So by mean value theorem, so once the hypothesis of mean value theorem are satisfied, you can assume the conclusion. So by mean value theorem, there exists a C on the open interval 0, 2, at which the derivative equal to f of b minus f of a divided by b minus a. So what is f at 2? F at 2 is given to be 4. What is f at 0? It's given to be -1 divided by 2. That is 5 over 2. So once these two conditions are satisfied, then by mean value theorem, you can find a C whose derivative f prime c is equal to 5 by 2. What is 5 by 2? It is slightly more than 2, isn't it? But the problem tells us that f prime x is always less than or equal to. So it is saying in the problem, f prime x is always less than or equal to 2. But we found a C at which the derivative is more than 2. So it should be smaller than 5 by 2, right? So this is not possible. So if you are able to find a C, that should be only smaller than 2 and not exceeding 2. So your conclusion here in this problem is there cannot exist a function f such that f of 0 equal to -1, f of 2 equal to 4, and f prime x less than or equal to 2 for all x. That is impossible. That is the conclusion. Please watch the rest of the videos in this section, in the section video. See you for my next video on 4.3.